Now we're going to continue. I'm going to cut this video into two parts. This is going to be the second part, which I might not, finish. So we're going to maybe see this next time. This is going to be about so-called integrated processes. Integrated processes are strictly, just to put it in simple terms, non-stationary processes with stationary increments. So a process is going to be integrated. Okay, this is how you denote this. It's going to be integrated of order 1 if it basically it has two things. Okay, number 1, it is not stationary. Okay, it's not going to be stationary, but the increments are going to be. So the increments are stationary. Okay, the differences, which are called increments, but the process itself is not. If this is the case, then the process is going to be called integrated, and I will explain what the order means. What the order means in this case that you would need to differentiate the process once and not more. Once. Okay? Differentiating it means differentiating it once and not twice to get a stationary process for the very first time. Okay? So if it would be required that you differentiate the process twice, so the increments are not stationary, but the increments of the increments are. You understand what I'm saying? So let's say you have the asset price, which is, number 1, returns are the increments. These are the relative ones, but it doesn't matter. And then you find that the returns are not stationary either. But maybe the increments of the returns are. That is the increments of the increments. Then the model would be basically integrated of order 2. Okay, so then the process would still not be stationary and the increments would not be stationary as well, but you need to differentiate the process twice. So that basically would tell you the order. I'm not going to find this today, okay, so I'm going to consider some examples to it. The random walk is going to be one of them. That is going to be an integrated process. Integrated process, you can use the term integrated process for synonymous for, or being synonymous for a non-stationary process. Okay, but that's not the same. Okay, so if it's integrated for the 1 or higher, then it's non-stationary. Okay, but it's not basically synonymous. Anyways, the random walk is a non-stationary process. You will see that over here. That's the definition. It looks like an AR type model, which it is, by the way. And there is also the random walk with drift. Okay, so there's another one, and for the drift parameter, you have a constant added to it. So that's that. Not a big deal. Okay, so technically the same. The random walk, for which basically you have the drift parameter, that's called, this is a different parameter. Okay, this is basically equal to 0 in that regard. Okay, so delta, that is the parameter. All right, that's it. So I'm going to discuss these processes a little bit. So I'm going to examine some properties, what are the issues with that. Now, first of all, it's not stationary. Okay. So one of the things that you would need to remember is when it comes to AR models, and that you'll see. Okay, now first of all, let me show you some paths. Okay, literally the random walk can be anywhere. Okay, in German it's called Irrfahrt. All right, so that's a random walk. So it can be basically observations can be anywhere, or the realizations of the process. You go like this, go like this. You might assume basically there is a linear trend in data, but it's not necessarily the case though. So from the path of the process, you cannot recognize whether there is a trend in the data or not most of the time. Okay, so these were basically paths of random walks that I was simulating. And so it can be basically literally anywhere. Okay, and of course, clearly these are non-stationary processes. That's for sure. Okay, because this is not how a stationary process would look like. Okay, but most of the time, when it comes to that, it's not always recognizable. Okay, so you cannot identify from the path whether the process is stationary or not. But in this case, if you have, let's say, sufficient number of observations, that is going to be possible. Anyways, I will show you how to test this next week, but not this week. Okay, now if you compare it to an autoregressive model, you saw that this is an autoregressive model, and I was using also a different representation for that. So again, with the time issue, just as I did basically for the Gauge type models, which I don't reconsider, this is how it would look like. Okay, so again, that was basically its structure. Now, focus on that one, please. It's going to be stationary if and only if the absolute value of A is less than 1. You might remember, okay? So that is clearly not true for the random walk because the random walk was looking like this, okay? So random walk is by definition a non-stationary process. Anyways, but I'm going to talk about something else. How would you get that? So if A is equal to 1, then there is a representation for the random walk. Of course, you would simply just replace A by 1, which yields in this process. Okay, it's not difficult to see that. And after that, you will have basically the constant times the sum of these ones, which is equal to 1, by the way. I mean, but no, sorry. So you have, this is going to be 1 plus 1 plus blah, blah, blah plus 1. And the question is how many times? You start from 0 and you end by t minus 1. So you have basically t somewhere in between. Okay, so that's going to be t. All right, so this expression is simply equal to t then. All right, so you have v times t, which yields in a so-called linear trend in the data. And then you have, of course, a to the power of t, which is a to the power, corresponds to 1 to the power of t. If a is equal to 1, that's equal to 1, of course, for the starting value. And then you have these noises. Now, regarding the noises, okay, and that's something that you should see here, the first summand is going to be obtained by setting j equal to 0, which is epsilon t, okay? And the last summand, and the previous one, the next one is going to be t minus 1, and the last one is going to be simply epsilon 1, okay? So you have epsilon t plus epsilon t minus 1 plus epsilon 1, or if you reverse it, epsilon 1 plus epsilon 2 plus epsilon t. That's the final one. You see? So I was basically changing the order because I don't like this representation. Okay, so but that's something which you might be recognizing as basically the noise, okay, from the first to its last observation. You see? Okay, so I was just, changing the summation index accordingly. And not just the summation index, but the index basically for that one. So again, this is just going to be a simplified version, and that's simply just the sum of these noises. Understand what I'm saying? Okay? Now, if you, and that's something that you might be considering, if you take the increments of that process, that means differentiating it. See what I'm saying? So differentiation is, of course, the current observation minus its path. Okay? What you're left with is basically, the current observation of the trend, which is v times t minus v times t minus 1, which is going to be simply just v. And then you have the starting value, which I dismissed because there is no starting value basically for the increments regarding that. So it would start by 0 by definition. And then you have these noises. Okay, and then you take out basically the sum until the last one, so this will be basically epsilon t. Okay, so plus epsilon t, and this expression is simply just the constant. See, so you have a constant plus the noise at time point t. These are the increments of the process, so simply just the noise. That's it. You understand? So the process is not stationary. But after the first differentiation, it is, because the noise is stationary by definition. You understand that, guys? Okay, so that is what it's going to be. So you need to differentiate the random walk once to get a stationary process first. With or without drift, it don't really matter. You understand what I'm saying, guys? Okay, so that's how it goes. So a random walk, with or without drift, it don't matter, can be also interpreted as a cumulative sum of these noises. You understand the term cumulative, okay? Okay, so this is the cumulative sum of these noises. All right? From the first to the last. And then you add them up. That's it, okay? Of course, that's not going to be stationary. But anyways, okay? So there is a linear trend in the data in this case. But if you look at the path of a random walk, you would not recognize whether it has a linear trend or not most of the time, to be honest. Okay? So it might be suggesting that it is, but it's not always clear. So you need to have a sufficient number of observations. Maybe that will be clear after that. But anyways, if there is no drift in the data, okay, and then you'll have basically v is equal to 0, then this is what it degenerates to. So, but there is still a cumulative sum of these noises plus a starting value some point somewhere. You understand what I'm saying? So that is an interpretation, representation of a random walk, representing it differently, not a recursive formula. Okay, so that's a recursive formula here. Okay, but that's basically, you know, in terms of the sum of these noises. So sum of noises, somehow. Okay, you can change maybe the variances and whatever. Okay, but that's it. This is the random walk. You understand that? Okay, now, cumulative sum, by the way. All right, so let's discuss it. So basically the process, as I mentioned before, is stationary if and only if the absolute value of this parameter is less than 1. And since basically we have equal to 1, that the process is not stationary. With or without drift, it doesn't matter. So even if the random walk has no drift, the process basically would be non-stationary one. You understand that, guys? I mean, as basically I mentioned before, okay, so that's how you also see it, but that's just not the way to do it. Okay, we can also discuss the moments, which I'm going to. So if you address the properties of a random walk, I mean, basically the moments, so first off by the mean, so what is going to be the mean of the random walk? Now, it depends on which kind of representation you use. I use basically, I mean, it doesn't depend on it, but from the practical perspective, if you take the random walk with the drift, okay, so you have basically that expression, so you have the cumulative sum of these noises, okay, so I was always using that one, okay, and since this is expectation of 0, I mean, just a moment, so let me start from inside. The noises have expectation 0, so the sum of zeros is going to be 0. That will have an expectation of 0, and that will basically the expectation of the model. So the expectation of the starting value plus the trend. Okay, so that was basically the expectation of the random walk. Now, if there is no trend in the data, so if there is no drift parameter involved, then the process is going to be time independent. Okay, so the mean is going to be time independent, of course, if and only if there is no drift, okay, for the random walk. So random walk without a drift is going to be at least mean stationary, but not the variance stationary, because the variance would always be time dependent no matter what. So the process will not be stationary, but at least it's mean. It would be if there is no trend. You understand that, guys? Okay, but if there is, that is going to be there is a linear trend. Okay, so this is a linear trend, the expectation of a starting value. You can argue that's the intercept plus the drift parameter times time. Okay, the drift parameter is the slope, basically, of the linear trend. That's it. Okay, but that's the drift. Anyways, okay, what about, I mean, let's see how this is, and this is not difficult. The expectation of a sum is the sum of the expectations, as you might see, and the expectation is of the sum is going to be 0 because the noises have expectations 0. Okay, that's not difficult actually to see. Anyways, what about the variance? Now, when it comes to the variance is always going to be time dependent, no matter what. There is time dependency of the variance, and that you cannot get rid of. Okay, so you can make at least the mean time independent, but not the variance. The variance is always going to be time dependent, for sure. Okay, now, how come? The variance of a sum is not the sum of the variances, but again, you can simply take out the additive constant, because the additive constant does not have an impact on the variance at all. And then you have the variance of a sum of the starting value plus the noises. Now, the noises don't depend on the starting value, so there is no correlation. In that regard, the variance of the sum is equal to the sum of the variances. And in addition, that is also true for the variance of the sum of the noises, because the variance of the sum is equal to the sum of the variances. So you can simply just bypass the sum operator because the noises are uncorrelated by definition. So, and if the variances, okay, each is going to be sigma squared, it's a constant variance, so you have t of them, because that starts from the first to the last one, and then you have, of course, t times sigma squared as a result. So that confirms basically this part here of that expression. Is it clear, guys? Okay, so that's not difficult basically to see. Now, again, let me repeat, the variance is going to be time dependent because because the random walk is not stationary. Or you can say the random walk is not stationary because the variance is going to be time dependent. That's a major issue. Okay, is it clear? And then something that you cannot rid of. Now, this is also not just time dependent, but let's say if you assume the starting value to be equal to a constant almost surely, then you can also say that the variance of the process is directly proportionate to time. So as time increases, so does basically the variance. Okay, that's why you see that type of tendency. Okay, so here or whatever here within that frame. Okay, so these were these random walks. It could go back up anyways. Okay, so the variance again of the process is directly proportionate to time. This is why these paths look the way they are. All right, is it clear? Okay, guys, yeah, so that's it. Now, what about the autocovariance? Have a look at that. This is also time dependent. And this is the formula, actually. I was not using that one in the script, but maybe you can illustrate why this is. So you choose the minimum of t versus t plus h, depending on whether you look into the future or the past, but it doesn't really matter. It's going to be time dependent. So that always depends on the point of time where you are. Okay, it also depends on the time lag, but predominantly in the time where you are, so you cannot get rid of that as well. Now, let me just basically show you why this is. So let's say if the time lag is greater than 0, which means that you look at the autocovariance of the current observation versus a sum of observation of the future. Okay, so let's say the current observation, and this is what it would be, okay, is equal to the sum of these noises. So you have the sum of these noises. Just ignore the starting value for a moment. You don't need to have it, but the sum of these noises, that's what we are up to. And if you go further, which means that you go basically further into the future, t plus h is going to be greater than t, okay? Obviously, because h is greater than 0. So you go further, that means that if you go to basically time step t, this is where you are, but you don't stop. You go further, basically you go to time point t plus h, okay, because it's further in the past, in the future of the process, t plus h is greater than t. But you'll see that these two don't overlap, so the noises that do overlap are here. These are the ones that do overlap. There is no autocorrelation between those and those. You understand what I'm saying? So in that regard, you can basically just take them out, and then the correlation of the sum is going to be, the covariance of the sum is going to be basically equal to the variance. So this is going to be equal to the variance of the sum of these noises, and the sum of these, the variance of the sum is going to be the sum of the variances, because noises are uncorrelated. The noises are uncorrelated, but these two overlap with each other. You understand that? Okay, so that's what you need to understand here. So therefore, you have, in this case, that's going to be the variance t times sigma squared, if you ignore the starting value for a moment. Is it clear? Okay, so in this case, if you go into the future, that's what it is. Keep in mind, the process is not stationary, so the autocovariance is not going to be equal to the autocovariance at time point, or with respect to time lag t minus h. Okay, so that's not the same. That's only true for stationary processes, by the way, but not for non-stationary ones in general. So if you look at that one, if basically h is less than 0, then of course t plus h is less than t. Okay, so you don't need to go that far. You are somewhere in between, because t plus h comes before t. Then you understand? So that's prior. And if you look at the process at time point t plus h, this is going to be some point of time where the noises would stop. So that would stop here, and then these noises would overlap. There is no autocorrelation between the noises that come after, so those and those. Okay, so there is no autocorrelation, obviously, but there is autocorrelation between those and those. That's obvious. You understand? So these two basically overlap, and the autocorrelation is going to be t plus h times sigma squared for those. Because the sum, the autocovariance of the sum is going to be equal to the variance of the sum. That's it. Okay, these two overlap and the others don't. So that's that. Okay, is it clear, guys? So if it's basically less than 0, then that is what it's going to be. And if it's greater than 0, then we saw that it's going to be t times sigma squared. Okay, now which one you would take, it depends on which is smaller. That's it. So if basically you go beyond, I mean, if it's greater than 0, then this is greater, so that's going to be the minimum. T is going to be the minimum. And if this is true here, okay, so if this is true, then t plus h is going to be the minimum. And that is consistent basically with these expressions. All right, guys, you understand this? And yeah, hopefully you do. And this is what it's going to be. Now, regarding the autocorrelation, what do you need for the autocorrelation? You need the variance, of course, which we just calculated. And you need the autocovariance. You simply divide the autocovariance by the variance. Okay? Now, what comes basically, it doesn't really matter, okay, whether basically t or t plus h is the minimum, because as you might see, as t progresses, the autocorrelation would converge to 1. For sure, no matter what. So at a given time lag, it doesn't matter. Is it clear, guys? It will basically converge to 1. And by the way, and that's not only true, so will the empirical one, but it will not converge to 1. It will converge in probability to 1. You understand, guys? Okay, so just in comparison, the theoretical one converges to 1, absolutely. But not necessarily the empirical one. The empirical one converges in probability to 1. And that's going to be an issue. You would falsely assume that there is a perfect positive relationship between a current observation and the past, which is nonsense, guys. It's not true, right? There is no perfect positive relationship in the long run. But the empirical correlation would simply just suggest otherwise. Do you understand how big of a deal this is? So there might be some problems regarding estimation of non-stationary processes. This might be indicating that. Okay, because you would falsely assume that there is a perfect positive relationship between the current observation and some future observation or some past observation, which is not true. It's nonsense. You understand what I'm saying? Okay, so again, that's what the theoretical correlation does, and that's what basically the empirical one does. It will converge in probability to 1. We talked about the asymptotics, by the way. Remember those, right? Okay, but we're not going to talk about them away. So autocorrelation converges to 1 by time, okay? Which is simply, I mean, that's illustrated from these. Just to take that and divide it by that, and that's almost identical, okay, right? But, so even if basically t plus 1 is less, but it doesn't matter. And the empirical one, the simple one, is going to converge in probability. So this is how you calculate it, okay, which I was recalling it here on this slide. That's a formula, right? And you can also take that for the random walk as well. And yeah, so as you might be guessing, this is converging to 1 in probability as the sample size increases, which generates some problems. Okay, so regarding the regression with non-stationary processes, okay, because that will be also true for regressions like these. Yeah, but as you might see, this is an issue. Okay, so one of the issues basically for non-stationary processes is that their autocorrelations will converge in probability to 1 in the long run. I mean, the random walk is an example, but there is more than just a random walk when it comes to non-stationary processes. Is it clear, guys? Okay, again, but there is also going to be other issues as well. And I mean, of course, if the correlation does that, then so does the coefficient determination within a simple regression. You understand that? Okay, so that means that the explanatory power of the regression would be equal to, basically would be 1. which is nonsense. All right, that would not be a stochastic model, by the way. But anyways, okay, you understand what the issue is. Okay, now this is not straightforward to show, so that is more, let's say, kind of advanced when it comes to convergence. But it's not that difficult to see. So because that expression looks almost like this in the long run. Okay, so when it comes to basically the time lag, there is not much difference. So as basically t increases, right, there is not much difference between the two expressions. Only just a little time lag involved here for the latter. That's the only thing that differs. Okay? But if basically the sample size increases, this effect is negligible, you know. So therefore you have convergence and probability, by the way. Anyways, yeah, that's it. So basically this is what it would be. Now in this case, the expectation of a sample mean of the squares, that has an implication, okay, is going to be something which is not going to be finite. Okay, so means it's not finite, it depends on basically on the sample size. Okay. Now, if the expectation is not finite, then this means that the arithmetic mean does not satisfy the weak law of large numbers. You might remember the weak law of large numbers, what was necessary for the weak law of large numbers, okay? So it requires the following. I mean, the weak law of large numbers, what does it say, okay? The weak law of large number would say that the arithmetic mean, okay, of basically of some sample, an arithmetic mean, converges in probability to the theoretical counterpart. Okay, so as the sample size would increase. You understand what I'm saying? That was a weak law of large numbers. We discussed this, I think, 2 weeks ago. Now this requires actually 3 things. Number 1, it requires the expectation of the mean would be finite. So the expectation of the mean, as well as basically the expectation of each summand, is going to be finite. That's going to be point number 1. You might remember the proof. That's why I was proving that using the Chebyshev inequality. I was proving basically the weak law of large numbers using the Chebyshev inequality. That was one. I mean, there is multiple versions of the weak law of large numbers, but if basically the expressions are IID, that the arithmetic mean of these IID summands would converge in probability to its theoretical counterpart. Now, the second is that the variance of these summands are also finite. And the third is uncorrelatedness. You don't need independency, but uncorrelatedness would be enough regarding the summand. So uncorrelatedness regarding the summand from which the arithmetic mean would consist of. Okay? Now, again, this was a requirement, so one fails already. Already the first one fails. Because as you see, okay, the first one is no longer finite as t increases. So as t increases, the expectation of a sample mean, which is, by the way, equal to the expectation of each, okay, which might be the case. I mean, it's not necessary though, but it might be the case. It doesn't mean that it's going to be finite. Now, how come? Basically, let me show you that quick. So because that is something that might be not intuitive. So the expectation of a linear transformation is a linear transformation of the expectation, right? And the expectation of a sum is a sum of the expectation. So I simply bypass the sum operator and the expectation of those, okay, so the expectation of the squares were basically the variance of the processes. Okay, so these were the variances. That's that. Okay, now the variance for sigma squared, right? So you have, no, sorry, that was for the random walk. The variance was time dependent, by the way, so with respect to time. So that was 1 by t times the sum of t times sigma squared. You understand? So, but t is basically the issue here, so you cannot take that out. So you have the sum of these, basically of these numbers from 1 to t. So let me take sigma squared out. So sigma squared times 1 by t times the sum of these t's, okay? And this sum, there is a formula for this. You might remember from so-called arithmetic series. The sum of all numbers from 1 to n is, you can prove that relatively easily, n times n plus 1 by 2. Okay, so y, again, that's not what the issue is going to be. So if you finish this consideration, I'm going to start off doing that over here. This is going to be sigma squared times 1 by t times the value of this sum, which is simply t times t plus 1 divided by 2. And if you basically, cancel t, then you'll find this is going to be sigma squared times t plus 1 by 2. Okay, so that's how you can derive this formula. But it doesn't really matter, because all that matters is the issue with t. So as long as basically if t increases, so is the expectation. So that means that it's not going to be finite by t. And if it's not finite by t, then it does not satisfy the weak law of large numbers, which is an issue. Why? And I'm going to show you later on why this is an issue. One of the reasons is, of course, the inconsistency of the estimation. You might remember what a consistent estimation is. So an estimation is called consistent, if basically the estimator converges in probability to its true parameter as the sample size would increase. Okay, but if it does not, so the mean of, or the sample mean of the squares does not converge in probability, which it doesn't, then there is no way to estimate the variance of a random walk by the sample variance. No way. That's what I'm going to summarize. So since basically the issue is that the sample variance, so the sample mean of squares relates to the sample variance, guys, because the mean of the squares is minus the square of the mean is going to be equal to the variance. Now, regarding the random walk without a drift, that would not be an issue, but if you don't have a drift, the sample mean of squares is going to be equal to the sample variance of the process. And the sample variance, since the sample variance does not satisfy the weak law of large numbers, because the sample mean of squares does not, so since expectation goes by time, goes by the sample size, the sample mean of squares does not satisfy the weak law of large numbers, that's going to be an issue. So it will not converge, in probability. It will be basically diverge. So there will be a divergence basically as the sample size increases. And that means that there is no way to estimate the sample variance, the variance of the random walk by using basically sample variance. So that's basically the implication. The sample variance is not going to be consistent when it comes to the estimation. It's not going to be even possible. You understand the issue, guys? So one of the things that the weak law of large numbers requires is to be the expectation to be finite of the sample mean, whatever a sample mean is. But if it's not, then it's not going to be. Do you understand that? So that's that basically. And there is no way to estimate the variance of the random walk using the sample variance, because it's not consistent, by the way. But that's just a side note. You cannot do it. It's impossible. And there is no way to bypass that in that regard. Maybe there might be some issues, but not in this way. That's also an issue regarding estimation of variances for non-stationary processes. There is time dependency, so you would need to take that out. But the question is how. Anyways, you could take a square here, right? For example. Then it would be finite, but that's not the sample mean. All right. So this is not how it works. Simply speaking. Anyways, this is what I wanted to do here. Is there any questions regarding to it, guys? To next week, we're going to discuss certain properties. I'm going to integrated processes. This is what I'm going to talk about next week, and I'm going to show you how to test stationarity. That is going to be also a basically a assignment of yours. Okay, guys, so that's what I wanted to do. And yeah, I want to stop here, and I hope you understand everything. All right. Yeah, thank you and take care. Bye.